Okay, hello everybody out there. We're very excited to chat with you today. Welcome to this MotionView and MotionSolve webinar series. In this session, we're going to be focusing on how MotionView and MotionSolve can help you with your automotive applications and just how easy it is to integrate these products. Your hosts today come from the Systems Integration Group as part of our global technical team. My name is Adam. I'm a Senior Solutions Engineer. And joining me today is the Senior Manager of the Systems Integration team, Ananth. Hey, Ananth, how are you doing today?
Hey, Adam. Hi, everyone.
So for those that don't know, we specialize in multibody dynamics for the automotive and defense verticals. We support our customers through one-on-one support, through consulting projects, through training, and content creation, such as this webinar. Sorry, I should have been skipping through. My apologies. Here's some more information about your presenters for today. Now, this webinar has been put together to showcase a broad spectrum of applications for our automotive and defense customers, but these topics do extend well beyond those groups. We aim to introduce you to MotionView and MotionSolve to demonstrate the guided processes, guided wizards, guided tools, and to showcase some of our advanced feature sets, my apologies, to take you beyond just rigid body models. Now, a little bit of housekeeping. We are going to reserve about 10 minutes at the end of the webinar for questions. As your questions may arise, please go ahead and add those to the chat, to the questions feature to either be answered on the fly by one of our hosts or to be answered during a discussion at the end, time permitting, of course. Now, before we dive into these demonstrations, let's do a brief review of the history of these amazing products with the help of Ananth.
All right, let's advance to the next slide. All right, so I will be super brief with history because it's important to frame this in the context of what has already transpired. So MotionView has been in continuous development since 1995. In 1996 is when the first release happened, and that is what we can frame as the US OEM, automotive OEM era. Primarily, MotionView has been and is still in use as a Adams pre and post processor. And it is based on a MDL, which is an ASCII file format. So this file format is human readable. It's hierarchical. It has memory of all the modeling changes that occur as you develop your model. And by definition, it's both guided as well as modular in nature. The solver agnostic aspect is also there. So as I said earlier, MotionView is still being used as an Adams preprocessor at some customers. In 2006, so early 2000s is when MotionSolve as the solver came on the scene, and that is when MotionView was developed with a tickle-based UI. So almost exclusively development of MotionView has happened for the mainstream with a MotionSolve focus. And that is back then we had mesh-based 3D geometry, but also external file reference-based assemblies. So 2013 to 2020 would be what we would call the modern UI era, where we went to a Python-based UI, and that is when we started supporting CAD-based 3D geometry. This also enabled us to have a little more closer integration with EDEM. EDEM is our discrete element method product used for characterizing bulk materials such as soft soil, sand, rocks, etc. And it's used quite frequently by our military customers for mobility simulations, as well as agriculture and construction. And other features also started being integrated into MotionView at that point. So since 2020 up till present day, we are focused on what we call verticalization, which means dedicated libraries for various industries and various applications. So as an example, in addition to the car and small truck library, which has been in development since 1995. We now have a machinery library, which is used for gears and bearings and things like that. We have a heavy truck library, which is really an extension of our car and small truck library. And we also have two and three-wheeler library as well. We also have native FMU support as well as live animation in the latest releases. So if we go to the next slide, where we talk about MotionSolve. So MotionSolve came a little bit later than MotionView on the scene, but it's been around since 2002. In the very early days, it was meant to be, not meant to have that close of an integration with MotionView. So it was really meant to be used in the finite element preprocessor world, which is hypermesh, of course. And it was sort of biased towards that. But then in 2008 to 2013, when what we call as the benchmark era, that is where we started to see large automotive OEM adoption. And that is where we started to develop MotionSolve with specific regard to the needs that large OEMs had at the time. Things such as Simulink co-simulation for controls, Adams compatible user subroutines, frequency-dependent bushings, and things like that. 2014 to 2019 is where MotionSolve saw a lot of development for co-simulation technologies. So OptiStruct, which is our finite element solver, EDEM I've already talked about, as well as AccuSolve, which is CFD. So these are things which started to develop sometime in the previous decade, end of the previous decade. And we also had Inspire come on the scene. Inspire is another product that we have which enables access to MotionSolve. And there we have primarily a Python-based framework. So 2020 to 2025 is when MotionSolve has seen widespread adoption, and that is where we've been able to drive lots of enhancements in the contact algorithms and developed advanced functionalities such as flexible body contact. And then later, real-time. So real-time simulation is now a reality in MotionSolve for both car and small truck based models. And in the latest release, we also have real-time code generation as well. So that's a little bit of history. Now on to a little more relevant topic here. So I will very briefly talk about common automotive workflows that MotionView and MotionSolve are today being used for. So if you see on the left side of the screen, those are all inputs to MotionView. So you have in the automotive world, there's typically either parametric geometry or CAD. There's some structure or finite element models. There's lots and lots and lots of component and subsystem data for all the different components that's there in an automotive chassis. And then we also have making it a little bit easy to integrate all of this huge amount of data is libraries. So we have both a wheeled vehicle library, which we'll talk about in detail today, as well as we have a tracked vehicle library, which we will not focus on today. So what can you do with this model that's been developed using all these inputs? You can, of course, do kinematics and dynamics. So things like K&C, kinematics and compliance analysis, vehicle dynamics simulations, durability simulations. Those are possible using in our close integration with both OptiStruct as well as the fatigue side of things. Mobility and bulk materials. So I already talked about EDEM. We also have a native soft soil model, which we'll talk about later today. And then 1D systems. So whether it's for controls, whether it's for modeling, things like active controls, active chassis components, etc. We have Twin Activate, which is Altair's 1D tool. And then another common workflow is packaging studies. So clearance studies around tire envelope and things like that, suspension components, envelope studies. And then lately, since 2024, we have X in the loop simulation, which is enabled via MotionSolve real time. So back to you, Adam. Let's take it away on the details of some of these things.
Perfect. Thanks, Anant. So speaking from my own experience as a former MSC Adams user and former ANSYS Motion user, one of the many strengths of MotionView and MotionSolve apparent to me and to other users are not only how feature rich the product is, but also how simple the adoption and implementation can be. Because of that, we've categorized 5 main areas that are frequent in a user's, I'll call it a typical workflow. And we've covered how easy it is for the user to achieve these goals. This includes how easy the product is to use, to explore, to enhance, to customize, and to integrate with other Altair and third-party products. Now, MotionView is extremely easy to use right out of the gate. With the intuitive user interface, which is going to either guide you through various processes, make simulation components visible and accessible, or automatically complete certain tasks for you. There's wizards for assembling half or full vehicle models, wizards for creating component test rigs like strut dynos and tire test rigs, wizards for creating leaf spring assemblies, wizards for tracked vehicles, wizards for flexible bodies. The list goes on and on. Now, simulation scenarios, automotive components, and example models can be quickly added from palettes to automatically generate driven and non-driven events, to add things like air springs, or to explore completed models of various classes. Event-specific automatic reporting, say that 5 times fast, is also available to quickly analyze results and without in-depth knowledge of post-processing. Now, we'll look at each of these topics with the help of a demo. Each of these demos are not being done live today. However, they are completed in real time to really give you a sense of the speed to which you can complete these tasks. Now, let's assume this is your first time using MotionView. You want to assemble a vehicle to get accustomed to the interface before you start off on a custom model. Following installation, the user can enable the Vehicle Tools extension, which activates the Vehicle Tools ribbon. Tools for assembling your wheeled and tracked vehicle model will now be visible. Now, this also enables the Vehicle Tools folder in the entity browser for adding automotive entities like tires. It'll also enable automotive events like the double lane change, and then it will also load example models like the UTV. To assemble a vehicle, we first need to pick an assembly library from our library wizard. By default, car and small truck is selected. Next, using our assembly wizard, with the help of step-by-step subsystem assistance, we can assemble a robust vehicle model from the various options displayed. And as simple as that, we've completed our first vehicle assembly. Now, a similar approach can be taken for adding standard automotive events to our new vehicle assembly. From the entity browser, you can go to Vehicle Tools, Events, Car and Truck to add single or multiple events that you can then modify after they're automatically generated in your model tree. Here, we've added a double lane change, a J-turn, a straight line acceleration, a slalom course, and an emergency braking scenario. All necessary entities for these events are automatically created and attached to standard assembly models. Now, you can adjust the size and speed of these events and apply event-specific outputs or solver settings. And then once you have your events defined or your duty cycle defined, you can choose to run some or all of the defined events to quickly evaluate the performance of your model. To review these results, you can apply a standard report to any standard event to automatically generate animations and plots relevant to your recently completed event. You can choose the reports tool, pick your event of choice, like the recently completed double lane change. A report will then be made with the help of Hypergraph and Hyperview. Now, the animation, along with, in this case, 15 pages of plots, are now automatically generated to evaluate the performance of the vehicle during this specific event. We can first watch the vehicle successfully complete our double lane change. We can then go into the session browser and review the numerous pages of event-specific plots that are automatically made. So without any in-depth knowledge of the software, a user straight out of the box can start creating robust vehicle assemblies, creating representative events, and generating meaningful results before learning the basics of multi-body dynamics. Now, significant workflows have also been condensed with the help of MotionSolve wizards. Leaf spring systems are commonly a pain to model from scratch, as they contain large quantities of bodies, joints, and contacts. Now, the leaf spring builder simplifies the definition of leaf springs with assisted design windows and CSV profile inputs. So you can build and test an assembly in isolation using this tool to ensure your assembly's target force deflection curves are achieved, for example. And then after verifying the performance, you can export them to an existing vehicle assembly and easily integrate them thanks to default parameterization. Now, another significant workflow is usually the creation of tracked vehicle systems. However, the generation of rolling systems, wraps, and contact geometry have all been alleviated with the 3-step track builder utility. Step 1 helps you create rolling systems like sprockets, idlers, and rollers. These can be single pin or double pin, singular or symmetrical, and they can use primitive graphics or custom CAD. Now, step 2 helps you wrap the rolling systems with a track, once again defined using primitive graphics or custom CAD. Based on the definition, the tool will let you know if the track will be long enough to complete the wrap based on the number of links, link geometry, and some other feedback as well. These can also be completed as a singular wrap or symmetrical wrap to further shorten the definition time. Now, step 3 helps you define the contact parameters for the wrap if you've chosen primitive graphics. You can choose to either auto-calculate the contact locations or manually define up to 5 point contacts to ensure the accurate representation of your tracked vehicle. Now, let's assume you've gotten your feet wet with the standard assemblies, but now you want to modify these models to better represent your ideal vehicle model. So in addition to the entity level modifications, you can modify your model from a subsystem level or at a property level, and then explore model improvements. You can easily make architectural changes to the model by importing existing subsystems like a front suspension variant that can automatically configure to your model through attachments. So this may be from an example model, or it's a custom subsystem you've created that you now wish to bring into a standard assembly. You can also flash the properties in your entire assembly model with a data summary sheet to update things like point locations, masses, stiffnesses, and more in existing entities. After you're done modifying the assembly, you can then easily study the performance of the model using HyperStudy to modify existing properties, improve kinematic and compliance results, or say limit handling behavior. Now, in this demo, we will import several existing subsystems into the same model to explore how easy it is to make architectural changes. So first, we're going to hide the rest of the assembly to isolate just our front suspension system. We can then go into File, Import, MDL Definition to import another front suspension. First, we're going to pick a one-piece McPherson suspension variant, set a name, and then hit OK. Now we can do that multiple times to then bring in a two-piece McPherson variant, a multi-link suspension variant, and a single lower arm two-piece variant. So once you have all of your variants in, you can activate the systems you want to use and deactivate the ones you don't. So now you can easily run an event with a front suspension variant and compare results to a previous architecture without having to carry multiple models. If you commonly use a system, you can save them as a user system now to import them directly from the entity browser. Now you can easily flash your entire assembly's properties through the use of the data summary tool. This table of values shows fixed and parameterized values for points, bodies, curves, bushings, springs, and more. You can import a data summary sheet to quickly overwrite some or all properties of your current model. Simply pick an SLK file and the configurations properties will overwrite the properties currently in your assembly. Now, just as easily, you can export a data summary sheet to save the current settings of your assembly, potentially for revision control or configuration management. Because these data sheets are in an ASCII format, non-MotionSolve users can update this data sheet offline or provide data sheets for configurations they may want you to compare to existing results. As shown here, the SLK file can be viewed either in Excel or Notepad, and it'll display fixed values or parameterized ones. Anyone now has the ability to create a new configuration for your model that you can then load in and test the performance of. You can easily explore new possibilities for your vehicle models by using HyperStudy. In this demo, we're going to use a shimmable front suspension model to optimize the shim sizes to hit target toe, caster, and camber angles. Now, first, we're going to isolate the custom front suspension and steering system that I prepared for this study. This front suspension has inboard and outboard locations that can be shimmed to adjust the suspension angles while using the standard lower and upper control arms and tie rods. Now, suspension shimming, it's a common application for in racing environments where, again, there's submitted hard points for the vehicle's design, but you're allowed to move them by a few millimeters to improve the performance of on track or to suit driver preferences. Now, first we need to evaluate this benchmark model. So we'll add a kinematics and compliance event. We'll run this baseline event. Now you can see once you create the KNC event, all the entities are automatically attached to the model. We'll be able to use a standard report to review these results. Now for the KNC event, it's going to make 6 pages of plots and again, a KNC animation. But in addition to this report, a suspension design factor report is created that's going to show KNC metrics like toe, caster, and camber, but for each time step. Now, with this benchmark completed, we can launch a HyperStudy session from the ribbon. We can use an existing setup, a HyperStudy setup, or make your own. In this case, we're going to use one I completed ahead of time. But this is where you're going to set design variables like the shim widths. You're going to set the responses of interest like toe, caster, and camber angles. And then how you want to evaluate the responses like set targets. We can study the change in the suspension angles with our shims by adding a DOE based on our setup. Now there's several methods to choose from, like a full factorial, a Taguchi, central composite. There's also runtime options like purging result data throughout the evaluation to save room on the disk. Now we can accept this setup and evaluate the tasks. Now we're obviously not going to sit here and watch a full DOE solve. So once it's completed, you can review the results and visualize the data to draw meaningful conclusions from your HyperStudy runs. Now, this model in particular and this process was used to prepare a suspension angle calculator. So race day changes, I should say, to the number and locations of shims can be applied to a vehicle to best perform each time it's on the track. Now, here's where things start to get a little interesting. After exploring vehicle models with rigid bodies and default tire models, the user can enhance the definitions of tires, add flexible bodies, and explore different deployment options. So the choice of tire model it's paramount. It's critical for predicting the performance of your vehicle over smooth surfaces, soft soils, rough roads, or large obstacles. So changing tire models, luckily, is as easy as choosing the right tire and road property file. You can add deformable bodies to your model by replace things like rigid control arms, for example, with flexible representations to better predict the load paths and peak load cases. all with the help of the Flex Prep tool and numerous tuning options. You can also convert your model to a real-time model with a single click to significantly reduce run times or to deploy in driving simulators without severing a digital thread or having to complete model reduction. Now, not all tire models are created equal, so applying the best option for each event is critical to a program's success. Changing models is as easy as modifying the tire property file chosen for each auto tire entity. Here we can see the front tire pair and rear tire pair property files changing from Fiala to MF Swift models. Now, after running the rough road event, you can see there's a noticeable difference in the MF tire output and the Fiala tire. Now, third-party options are available as well, including F-Tire and CD Tire. Depending on your selections, more tire definition options will appear in the entity browser. So let's change the tire property files for the front and rear tire pairs again, but this time to CD tire models. Now, once again, we can compare results to see how the durability tire model compares to our original runs. So deformable soft soil models can also be activated with an appropriate tire property file and road property file. You can choose a soft soil tire model and a soft soil road file for the front and rear tire pairs. Now, the tire and road file must feature the soft soil keyword and parameters to be able to use for this analysis. Advanced features can be activated in the road file, such as multi-pass effects and bulldozing effects. And these soft soil road files, I should also mention, can be used for both wheeled vehicles and tracked vehicles. So after we've assigned a tire file and road file for our tire pairs, we can then go ahead and visualize our road using the Road Tools utility to make sure that our soft soil road is positioned properly. Once our graphic is created, we can attach it to the road reference marker. I believe it'll be on the front left in this demo, to make sure that the graphic you brought in does represent what your tire models are actually going to encounter. Now, for events, you can choose to use the road file set by default in the auto tire entity, or you can assert a new road file for each event. So after applying our soft soil entities, we can simulate the event, we can review the results, and then you can easily see the deformable soil interaction with multipass and bulldozing effects active to predict the trafficability of this pickup truck. Adding flexible bodies to your model can better predict loading into key components like a lower control arm. In this demo, we're going to use the Flex Prep tool to guide us through the generation of a linear flexible body. First, pick an FEM file of a meshed part. We can then add RBE2 spiders directly from the Flex Prep tool to add or just review interface locations for this component. Here, we're going to add one more RBE2 element to the outer mounting location. Once we're done, we can save the FEM and exit back to MotionView. We can choose an output file for the H3D flex body file, specify the interface node IDs. We can also include advanced options like stress and strain recovery. And then we can generate the flexible body. You can review the frequency modes directly from the user interface. You can obviously also review visually using Hyperview. Now, once we've created this flexible body, we're going to want to add it into our model. So first, we're going to change the lower control arm from a symmetrical body to an asymmetrical body pair to break the symmetry. We'll give some physical properties to the right-hand lower control arm, like mass and inertia. Now, for the left, we can now check off the flex box and pick the newly generated H3D file. This will also produce the mass and inertia properties for this part. Now, using the Nodes and Modes tool, we can review the interface nodes and their alignment, along with the participating modes and their current damping ratios. So after completing only a few steps, you can now simulate the model to generate results with this flexible left-hand lower control arm, completing a kinematics and compliance event. Now, after flex body definition, you can always rigidify a part and see its original performance again as a rigid body without having to undo any of the flex body definition. So we can rigidify our lower control arm and run again to see the change in performance. Now back here in Hyperview, we can easily compare the results of the flexible control arm to the rigid one. Now, real-time is a very exciting option for many customers as it gives benefits to multiple types of deployment. With a single click, the model can be prepared for real-time use without the loss of features like flexible bodies or limiting the degrees of freedom. There's no need for calibration, so a user can then solve in real time or faster to take advantage of the speed upgrades. Now, this can be used to shorten large design study runtimes just by reducing the simulation runtime. Now, obviously, the other main attraction for real time is the ability to deploy it in software in the loop, hardware in the loop, and driver in the loop configurations. Now, you might have atypical processes that you want to deploy automation, or you want to create your own wizards, just like the standard wizards and tools we've already covered, to save you lots of time and effort. Now, for that, you can easily write your own scripts, you can make custom libraries, and you can create your own user interfaces to significantly reduce development and evaluation time. Scripting of various languages can be imported from within MotionView to make model updates or even script the creation of entities and assemblies. Custom assembly libraries can be created to tailor options shown in the assembly wizard to only reflect your current platform and simplify assembly. And also, end-to-end processes can be created with tools like Altair Compose to automate the creation, simulation, and evaluation of models. Scripting can be an easy way to standardize models or to complete repetitive tasks. Simply go to File, Load Script, or Python script to quickly add, remove, or modify entities in your model. Scripts can either be in TCL, OML, or Python. In this example, scripts are being imported to change the color scheme of the model, then to modify the hard points of the front suspension, and then to modify the hard points of the rear suspension by actually importing a data summary sheet. There it is. Now, custom libraries can be created to tailor the assembly options for the user. In this example, our Formula SAE library was created for students to assemble a vehicle suitable for competition, but this can be done by any user to function as a working repository and have it reference an online location. After linking a custom library, the assembly wizard now displays subsystem assembly options as detailed by your custom wizard. This can also be used for revision control, where a library is set to show subsystems like front suspensions that have already been tested or are part of a design study. It should be mentioned that this Formula SAE library is available for download on our community website. Now, entire workflows can also be automated with tools like Compose, where features in MotionView can be enhanced as needed. In this example, an electric motorcycle prototype was being evaluated across several events of changing sizes and speeds. So this event DOE tool was developed to complete the vehicle fingerprinting exercise and save the customer valuable time and energy. First, the user can select a parent MDL file and the script will extract the solver decks for each event that's currently defined in the model. Multiple MDLs can be used to generate up to, in this case, 10 different simulations to use for the study. Now, after all the decks have been generated, an output directory is picked, and the XML decks are then multi-selected. The script will look into the XML files, auto-detect the type within. Based on the event type, default values for the size and speed of the event are then asserted. The user can modify the bounds of this DOE as needed. Now, the DOE can then be launched, and the progress and failure rate can be displayed as it solves. After it completes the DOE, a list of failed runs is showed. Automatic post-processing is also completed, with plots of generic and event-specific data created. Here we can see a series of plots converted to images for review. Now, also to round it out, a fingerprinting report card in CSV format was produced to summarize event-specific metrics. So an additional strength of MotionSolve is how easily it can be integrated with other solvers, such as OptiStruct, EDM, and TwinActivate, and third-party options as well. Nonlinear flexible bodies can be introduced to improve on flexible body performance during yielding. Bulk material simulation can be completed using EDM to better predict the off-road mobility of vehicles and performance of obstacle negotiation. TwinActivate can be used as an FMU or as a parent model with the MotionSolve as an FMU to define complex control systems. Now, in specific cases, the linear behavior of modal flexible bodies may not capture the behavior needed for your model. In this newest release, nonlinear flexible bodies can be introduced using OptiStruct. In this demo, we're going to replace a spring element with a nonlinear flexible body spring. First, we'll deactivate the coil spring system, and then in the front suspension system, we'll add a new body for the OptiStruct spring called OS spring. We're going to enable the flex option and change the function source to OS flex body. We can set the input to OptiStruct method and use specified FEM file and choose our prepared FEM file for the spring. Again, this is all prepared beforehand. To attach it, we're going to add 3 ball joints to constrain this flexible body. They're going to connect the OS spring to our lower control arm first. We're then going to attach it in 2 more locations, both from the OS spring to the vehicle body. So with the constraints supplied, we can now set the interface nodes for this nonlinear flexible body using the Nodes and Modes utility again. First, select the body, OS spring, and then select the Nodes and Modes tool. Under the Nodes tab, you can insert the node IDs from the FEM file to dictate where the ball joints connect to the dependent nodes. Here you can see the 3 nodes being defined. Now, since we deactivated the right spring as part of our original spring pair entity, we'll have to add a single spring back in for our right side. We can attach the spring from the vehicle body to the lower control arm. We'll give a linear spring constant of 120 newtons per millimeter. We can also change the appearance of the spring to match that of the left side, technically just for show. And then we can also set the preload to use force and length. Now we'll set the preload force of 7,000 newtons to generate the appropriate ground reaction force. Now, always remember to save your model. And then once that completes, we can launch the simulation from MotionView to prepare it for coupling. Now, since this is a coupled simulation, we're going to have to open the compute console and then launch OptiStruct using the FEM file generated for the event simulation. When the simulation completes, obviously you can then load the results into Hyperview and visualize the change in performance. You can also easily predict the off-road trafficability of vehicles using EDM for discrete element modeling and PM Flex Tire for deformable soft soil tire models. In this demo, we're first going to change the Fiala TIR files to the PM Flex Tire FXT files. Now, additional options for the tire file definition will appear in the entity editor. Next, we're going to select a large pothole-shaped road file to act as the entrance and exit into our soft soil pit. We can visualize the road, again, using the Road Tools utility to make sure it's located properly. Now, the size of this road should look to be able to accept the material bed from EDM. Now, if we flip to EDM, we can make sure that the soil bed is sized to fit into our large pothole. Back in MotionView, you can select the AutoTire entity and then select the Generate Files button to start creating the PM Flex Tire objects. Pick a CAD file for the shape, an output directory, and pick the Flex Tire converter executable. Finally, use the sliders to adjust the mesh, rim, and belt sizing. So now it's time to begin coupling this simulation. In EDM, we'll turn on the coupling server. Now in MotionView, we're going to use the EDM tool in the ribbon to create an EDM system, and then select the graphics that we want to have communicate with EDM. Here we can select the vehicle body from the view screen. And then from the selection helper, we can also pick the tires. Now, if we switch back to EDM, we should now see the geometry imported. Now, when it completes, we need to set the Flex Tire rim geometry to be children of the tire geometry. For the tire entities, we need to make sure they're set to be Flex Tire with the checkbox, and then also to add an inflation pressure. Back in MotionView, we can add a straight line acceleration event from the entity editor. And then we can now simulate the coupled model. Now, when it completes, in Hyperview, we can review the MotionSolve results. And then in EDM, we can review the bulk material results. Complex control systems can easily be inserted into your vehicle models using FMUs or functional mockup units, such as from Twin Activate. In this example, we're going to add an air spring model from Twin Activate into this pickup truck assembly. Now, rather than use an extremely complex expression in MotionView, this air spring can be modeled in this block style for increased readability and functionality. Functions for the volume and pressure can be visually defined, and a set of global variables can capture the static values. Now, this model can easily be exported as an FMU, which only requires one input for spring length and one output for spring force. After exporting, we can then go into MotionView. Oh, sorry, we have to generate it first. Now in MotionView, we can insert a rear air spring subsystem into this rear suspension system. First, we need to delete the default coil spring system, then go to File, Load MDL Definition, and pick the air spring subsystem that was prepared ahead of time. Now, in this system, you'll see it already has a coil spring with no stiffness, but it'll also have two FMU entities in it, one for the left air spring, one for the right air spring. as well as an actuation force pair coming from the FMU output. We can go into the FMU entities, pick the air spring FMU we just generated. Now, using the edit tool, we can set the solver variables and expressions to use for the input and output of this FMU. So now we can run this model and we can review the change in performance from our air spring functional mockup units. And that's going to exhaust all the material we have prepared for this webinar. Thank you everyone for listening along, and thank you for the questions you may have submitted along the way. I hope you guys enjoyed this webinar. And regardless of whether you're a beginner to MotionView and MotionSolve, or you're an established user, or if you're just interested in becoming a user, that this session was able to showcase many of the advantages and strengths of this multi-body simulation tandem. Now, from what I understand, many participants have submitted questions for this Q&A period, either beforehand or during the session. So, Anand, do you want to pick a few of these questions so we can try to speak to them here as best as we can?
Yeah, I think we'll have to pick a few questions because Adam, I think you have failed to put everyone to sleep, judging by some of these questions.
That's good. That's good. That was the whole plan.
Yeah.
I'm happy to hear that.
So we have 13 minutes, so I think we'll have to prioritize a little bit. So first question, can MotionSolve automatically iterate the hard points of a suspension if the range of roll center and other metrics are provided and the region for iteration is specified? Great question.
Of course. Yeah. So I would say very similar to the shimmable suspension model. A similar approach can be taken where you would parameterize the hard points, and you would be able to use hyperstudy. You would be able to give the design variable certain bounds. So you'd be able to give a plus or minus in X, Y, and Z, for example. You would be able to then evaluate the change in roll center, for example, and then obviously promote it towards a certain target.
Yeah, since the integration between hyperstudy and MotionView is all UI based, there is no coding involved here, so you can do almost everything. Not almost everything, actually everything, without writing even a single line of code necessarily. Okay.
Yes, exactly.
Next question. How do you set up a tire model independently instead of simulating a full vehicle? And then a related question actually is, what are the requirements for a tire test rig and what data is needed for accurate modeling, vehicle modeling?
Ooh, okay. So those are a couple of good ones. So for the first question, we actually have a standard assembly. It's called our tire test rig. So obviously that speaks to question 2, but in your assembly wizard, not only can you pick from half car or full car, but there's also a component level assembly you can make. One of them is the tire test rig. Now, once you have it defined in terms of what do you need for the tire test rig, you're going to need as much physical data as you have or as you can get. So the mass of the tire, the rim, you're going to need a tire file to obviously attach to it. Now, sorry, can you say the second part of that question again? Is it for accurate vehicle modeling or just tire modeling?
Yeah, so the question says accurate vehicle modeling, which I think we've somewhat addressed in this webinar, right? Okay. So maybe we can focus just on the tire part of it. What type of tire models do we have and things like that? Because there's a few questions on tires here, which are all related. Yeah.
So obviously we support a large array of tire models, both Magic Formula based and then also higher fidelity offerings like CD tire and F tire. From our installation directory, we do have a default library that you can pick from for some of these tire offerings. Now, some of them are an additional cost for licensing, but the information you need is, you're likely going to have to get a tire tested to build out an entire tire model to have the utmost confidence in it. But if you're early on in development, it's something where you can just take one of the tire models that are going to be representative of what you have, and then more or less worry about it farther down the line.
Yeah, so elaborate a little bit on that. Fiala as well as MF tire, which comes from Siemens. Both of these have reduced data requirements. So with as few as five to 10 parameters which describe the characteristics of the tire, you can start a full vehicle model. There's no need for to wait for an empirical data set that's required for all the advanced tire models. So that's something you can get started with really easily. All right. So next one, let's switch gears here a little bit. What approaches exist for modeling air bellow suspensions in dynamic scenarios? It's a good one.
So that's a good one. We technically already covered it in a way, in that the that twin activate FMU demo that I did was an air spring model. Now that was technically an example from last year, but in our newest release in our vehicle tools library, there actually is an air spring entity that you can apply. So you don't have to worry about creating your own entity or creating your own FMU. So it's literally just drag and drop right from the palette. Now, just speaking more in generality, if there was an entity that you didn't have that was not necessarily an air spring, but something that wasn't available from the palette, you can always define these types of entities either as a force with expressions, with a user-defined subroutines as well. So, if it's not available as a standard entity, you can essentially build your own entity, either again with subroutines or FMUs.
Great. So here's sort of a curveball for us.
Oh boy.
Are there any curve-based conceptual suspension models, meaning wheel position and orientation are defined by parametric curves instead of physical components? I can take that one, and sure. Maybe you can elaborate, Adam.
All right.
So the answer currently is no, we do not. But also, on that topic, stay tuned, because now, as you know, Altair is owned by Siemens, and Siemens has some interesting offerings there. So there is a possibility in the future where we could offer that type of thing, where you describe the suspension characteristics with parameters instead of actually duplicating or modeling the physical architecture of those components. Great question.
Yeah, because you'd be able to use something like a kinematics and compliance tables. So you essentially take the 3D element out of it, and you'd be able to just describe the motion ratios between your sprung and unsprung components.
That's right.
Yeah.
Okay, so here's one. Is it planned to make the event static load analysis also available for motorcycles in the future? That's an interesting one.
That is a good one. I don't know off the top of my head if that's a plan, but based on that question right there, we can definitely reach out to development and add it as a feature request. These types of things, if it's not currently available, by all means, you can reach out to us, and if there's obviously enough interest for features like that to get added in, we'll take all the feedback you can get. So that's something that right after this webinar, I can put in a feature request for that.
Very nice.
Or they might be already ahead of the game and plan on putting it in. I have to find out more.
Yeah. So how can we analyze tractor implement interactions? So these are for plow and cultivator applications, for tractor dynamics, weight transfer, wheel slip, and tire soil behavior.
Ooh, that's a lot of good questions. So obviously that speaks to a lot of our agricultural verticals, which hopefully we'll be able to put a webinar on for that vertical as well. Um, Now that's typically done with EDM. So for the bulk material simulation that we showcased here, you would have a multi-body tractor model, multi-body instruments that you might be using to interact with the um, with EDM. Now, I should mention that there are likely already a lot of models on our community page um, that are examples of, again, this tractor implement interactions. I want to say there's already cultivators and at least plows examples as well. But typically, that's the coupling that's done for those type of simulations.
Great. Next question. So this is an interesting one. Why were the results between Fiala and MF Swift so different, assuming the tires were identical? Is this a case of fidelity or something else? I think it's fidelity.
Yes, yeah, it's exactly fidelity. We do have essentially recommendations for different use cases for these tire models. Not all, like I said, not all tire models are created equal. Some have better applications than others. Fiala more for flat road limit handling type simulations. When you start moving into the rough road ride and durability type simulations, that's where you more trend into the higher fidelity offerings. So there's going to be a completely different number of inputs for parameters and things between these different tire models. So depending on your application, if you're unsure, I'm in our help documentation, there's going to be essentially a best use case chart where you can follow, depending on what you want to complete, what's going to be the best suited tire model for you, and which ones may also be suitable, but not as favorable.
We've got 2 minutes left here, so let's address maybe a couple more.
Oh,
How can MotionSolve
lightning round?
lightning round? Yes.
Yeah.
How can MotionSolve results be coupled with other solvers? For example, durability simulations.
Oh, that's a good one. So, I mean, typically for durability analyses, that's something where it's like a results handoff, I would say. So the multi-body model is being used to generate your peak load simulation or peak load cases. You may want to introduce things like flexible bodies to, again, better bound what the load paths and things might be. But once you have the results generated, you'd be able to pass into something like Hyperlife, where you can then figure out, component life based on, some structural analysis. Now, that's if you're doing it as more of, I would say, a handoff. Now, in terms of coupling, we did demonstrate that a little bit here today, where, you can we coupled with EDM, we coupled with OptiStruct. So from a more technical standpoint, that's usually done with our compute console. But yeah, durability is more of I don't want to call it an over the wall type process, but it's usually done sequentially. Where again, the results that come out, they're going to be in PLT or ABF formats. So like PLT is an ASCII file. So pretty much anything is going to be able to read in that time series data and then do those types of calculations for you.
Right. All right. I think we're out of time. I think we can probably take some of these questions offline.
Yes.
In our follow-up email, we'll try to answer some of those. This was great.
I agree. So I just want to take a second to thank everyone for attending. As Anant said, if you have any other questions, you can reach us by email. I believe there's a survey that's going to come with this webinar as well. So if we didn't get to your question, by all means, submit it again, and we'll do it all offline.
Yeah. Great. Thank you very much,
Excellent.
everyone. Thanks for attending. And we'll see you at the next webinar.
Awesome. Have a good day, guys.
Have a good day.